let me go around and look at people's papers.
Wait, that way.
And I'm gonna get real lazy balances. Like, I don't think I'm all IUPAC on the alkoxide name, but good enough. Hydrogen and sodium isopropyl oxide, alkoxides. One reaction we looked at yesterday. What other reactions did we see yesterday? Formation of alkoxide ions. All right, any questions on that? Name an alcohol more acidic than water. Most of them are in this range. There's water. Here's this phenol. 100 million times. I said 10,000. I should get no points. Huh? There's the phenol. pK of 10. All right. Can somebody tell me how to form an alcohol? How can we form an alcohol? It's a good way to make an alcohol. Well, maybe you're going to say fermentation, destructive distillation of wood. Then we got methanol, grain alcohol. That's not what I'm asking for. What do you remember from the alkene chapter in the fall? Oxymercuration. Are you looking ahead in the slides?
I was not ready.
All right, yeah. A reaction with an alkene. Could you make one with an SN2 reaction or an SN1 reaction? SN2 works good. Any of those? So here we go. Nucleophilic substitution of an alkyl halide. Good way to get an alcohol. Addition of water to double bonds also produces alcohols. Of course, these can suffer from rearrangements. And you learned last year that oxymercuration, demercuration gives you Markovnikov regio selectivity and stops carbocation rearrangements. And then, of course, the hydroboration oxidation gives you anti-Markovnikov regio selectivity, and the regio selectivity and stereo selectivity. You know the difference between those, right? Regio selectivity, stereo selectivity, syn addition, that's the stereo selectivity, anti-Markovnikov, that's the regio selectivity. All right, don't want to beat a dead horse, but look what I wrote here on my slide. Chapter 8, all those good things. Vicinal diols. So we went over how to name those yesterday. And you learned how to make them in Chapter 8. Syn hydroxylation of alkenes, osmium tetrachloride, followed by hydrogen peroxide, cold dilute, basic potassium permanganate. And here's the anti, which is peroxy acids, where you form the epoxide, then followed by base for acid hydrolysis, ways to get to the diol. So now we get to learn something new. Michaela, I think a year ago in fall, we did some of this before second semester, if I remember correctly, that far in the past. Organometallic reagents. What's special about those? Carbon is negatively charged and it's bonded to a metal, magnesium or lithium, and it will attack any partially positive carbon. So an alkyl halide, the halogen's electronegative, puts a partial positive charge in there, and the organometallic reagent go after it. It'll also go after carbonyl compounds, and a bunch more we'll see later on. And so chemists get excited anytime you can form a carbon-carbon double bond. A carbon-carbon covalent bond. Now, from last fall, where have you seen a carbon anion before?
Carbon positive.
No, a correct chemical species. Well, what is the most acidic hydrocarbon you can think of? The most acidic hydrocarbon you can think of. All right, let's back up. A trend for acids is the element containing the hydrogen. As that element becomes more electronegative, Does it become more acidic? Is it easier to give up the hydrogen? Think of, HCl. And I could put fluorine here. Let's do fluorine because it's in the same period. We say this is a stronger acid because this is nice and electronegative, likes the negative charge. Oxygen's very electronegative. It likes the negative charge. All right. Which is more electronegative, sp2 hybridized carbon or an sp3? It's a good thing we're having this review. Everybody forgot their acid-base chemistry. My heart is breaking. All right, this is more electronegative. What's even more electronegative would be sp hybridized carbon. And what kind of base did we like to use to pull this hydrogen off? Sodium amide. Looks something like that. Here is pretty much an organometallic reagent, sodium acetylide ion. And this would attack alkyl halides, carbonyl carbons, all that good stuff. So recall chapter 9 from last fall. Here is the most acidic hydrocarbon, alkyne. Sodium amide pulls that off. And then here we see it reacting with alkyl halide, forming a new covalent bond. So if you understand this chemistry, you're going to understand the other organometallic chemistry. Terminal alkynes can be converted with sodium to a sodium acetylides by treatment with an unusually strong base like sodium amide. These sodium acetylides are useful nucleophiles reacting with alkyl halides and carbonyl compounds to form new carbon-carbon bonds. So on to the Grignard reagent. So the other day and this morning when we looked at forming what did we form? We formed alkoxide, very strong base, and we didn't use an acid-base reaction to form that. What we used was a redox reaction. So I think it's fascinating that redox reactions are used to form some powerful bases that you couldn't otherwise get. So here we see magnesium in its elemental form, so it has an oxidation state of, my mic's never going to pick that up. Zero, yes, thank you. And over here it's in its usual state of +2, and we see the +1 because of the halide having the -1 charge. Alright, so here is the Grignard reagent, and we call it an organomagnesium halide. And so we write this down on paper, and our observations say nature is really like this. Here is our carboanion, and it turns out you got to use ether. This thing's actually kind of complex with the ether. They stabilize it. Fluorides don't generally react. Iodides, very reactive. These three halides all can be. And we can form a Grignard with a primary, secondary, or tertiary alkyl halide. So another metal that very active and can be oxidized and form a Grignard. We only call the magnesium compounds Grignard reagents. An organolithium reagent is lithium. So reactive metal, alkyl halide. Looks like we need two equivalents. One equivalent comes off and balances out the halide, and then we get our organolithium. And once again, there's the business end of the reagent, that lone pair of electrons. And we can make Viney, or our real halides, just like Grignards. And for this setup, we don't necessarily need an ether. We can use some other solvents. Do you think you can use protic solvents to make organolithium reagents? Protic solvents to make an organolithium reagent? Our favorite subject, acid-base chemistry. The answer is no, absolutely not. These organometallic things are super strong bases. How do I know this is the strongest base known to mankind? What if this is ethyl lithium? Well, the corresponding conjugate acid would be ethane, an alkane. What's the pKa of an alkane? Alkanes are the weakest acids known to mankind, and they have a pKa about 50. All right, so if you put one of these Grignards in protic solvent like alcohol or water, it just protonates this, and it's done, and then you have lithium hydroxide. All right, so all the solvents, all your Grignards using ethers, THF, and things like diethyl ether, organolithiums. You can use a few other compounds. So that previous slide said an aryl alkyl halide. Here, this bromobenzene would be an aryl alkyl halide. And so you can imagine a lone pair of electrons there, and this thing really wants to find a nucleus. So here's butyl lithium. I never had the pleasure of working with butyl lithium. In graduate school, some of my fellow students had the opportunity to work with it, and you have it like in a syringe, and when you shoot it out into the atmosphere, it reacts with oxygen and it bursts into flames. And I've always wondered what was in a flamethrower. I don't think it's butyl lithium, but fun stuff to play with. Very reactive. So addition to carbonyl compounds, you want to imagine that lone pair of electrons slams into there, those electrons jump out, and then you have a alkoxide. We might call it a magnesium alkoxide salt, and then you add some acid, and this thing gets protonated, and you get the corresponding alcohol. There is the corresponding alcohol. So in chapter 9 we had compounds with triple bonds here, but now we can have a fully saturated alkane group here if we need it. So we can use a Grignard reagent and formaldehyde, and we can get a primary alcohol that is one carbon longer in chain length than whatever carbon chain we have here. Imagine that slamming in there, those electrons jumping out, and we have this protonate. So there is a primary alcohol. So if we want a secondary alcohol, we can go from formaldehyde to some other type of aldehyde. So there's an alky group here. Once again, slams in there, those electrons jump up. We get this intermediate protonated with some acid, and there is a secondary alcohol. Addition of a Grignard reagent to an aldehyde followed by protonation produces a secondary alcohol. So for fun and no prizes, what do you think you need to react a Grignard with to get a tertiary alcohol? I'll give you a hint. It's a carbonyl compound, aldehydes and ketones. Absolutely. Aldehydes and ketones. So two alky groups. Third alky group slams in there. Alkoxide intermediate, protonated, and then there is a tertiary alcohol. Well, we have a whole chapter come up, probably in April, on carboxylic acid derivatives 1 now. Replace the OH with a chlorine atom and you'll have what's known as an acid chloride. And here we have two equivalents of the Grignard. Slam one in, slam in another, and then eventually you will get to a tertiary alcohol. And here's an ester, another carbonyl compound, two equivalents. Both these give tertiary alcohol. Now, how does this actually work? Here's the mechanism. Attack of the organometallic reagent on carbonyl carbon, and you get this intermediate, and you see the electrons jumping out on oxygen. Looks fairly normal. What are the properties of a good leaving group. What are the properties of a good leaving group? Man, people lost their minds. They don't remember anything from fall. Good leaving groups, are they strong bases or weak bases? Acid-base chemistry again. It keeps coming back to haunt us. A good leaving group is a stable base. That generally means weak base. Water is a good leaving group. And, of course, chlorine is a good leaving group, because it's the conjugate base of HCl, which is a strong acid. It means this is nice and stable, not much of a base, so it's a stable base. Alright, so we see we add one of these to the acid chloride and we form a ketone. And then we just saw how Grignards can react with ketones and give us tertiary alcohol. So here's our second equivalent, slamming in there. There's our alkoxide, protonate that. So I really hate this next little section because it makes a big liar out of me with leaving groups, because we're going to have a leaving group that's a super strong base. So I think there must be another explanation. It'll come to me when I'm lecturing. Here is the mechanism with an acid chloride. We saw that an ester, the same thing happens. Same thing being we get a tertiary alcohol. So one equivalent of Grignard adds, and we have this intermediate. And I can rationalize this, that this is a weaker base than this one. I can say, an alkoxide isn't necessarily a good leaving group. I don't see equilibrium errors, but I'm going to imagine that there are some, to say that nature will allow this. And then here's our second Grignard reacting, and we get our tertiary alcohol. So last fall we saw if we had an alkene and added a peroxy acid, we could get an epoxide. This is the common name for an epoxide, ethylene oxide. Well, at least 2-carbon epoxide. So the electronegativity of this oxygen here makes these 2 carbons a partial positive charge. Beginning of this section we said these 2 unpaired electrons here want to find a nucleus of an atom, so it has a positive charge, so that slams into there. That opens up, protonate that. So here's a good way to get a primary alcohol has a carbon chain that's 2 carbons longer than this one here. Alright, so butyl magnesium bromide, we got a 4-carbon chain. React it with ethylene oxide, we're going to get a 6-carbon chain. So here is 1-hexanol, old IUPAC. Hex 1-ol, hexane 1-ol. Grignard and lithium reagents will attack epoxides and open them to form alcohols. The reaction is favored because of ring strain present in the epoxide. That goes away when it gets opened. The reaction is commonly used to extend the length of the carbon chain by 2 carbons. Once a person forms a lithium compound, there's a whole slew of other metals you can react it with, and sometimes it kind of calms them down a little bit and they might be a little gentler, and you can do a bunch of interesting type of reactions. So here's a organolithium compound, and here's copper iodide, and we get this thing called a Gilman reagent after Mr. Gilman, who worked this out. And then once you form a Gilman reagent, we can form a carbon-carbon bond between 2 alkyl groups. So here's an alkyl halide, the Gilman reagent. So one of these R's gets connected with R prime. So there's the holy grail of organic chemistry, forming carbon-carbon bonds. You just hook up 2 alkyl groups. If you want to couple 2 groups together efficiently, you can use an organocopper reagent, a lithium dialkylcuprate, to couple 2 an alkyl halide. Maybe I should clean that up. Here's the alkyl halide. We're coupling this to an alkyl. I guess this gets wasted. So here is your acid-base chemistry warning. All organometallic reagents are very strong bases. That's why I asked the question about the protic solvents. Protic solvents will kill organometallic reagents. Alright, limitations of organometallics. Grignards, organolithiums, cuprates are good nucleophiles. That's why they do what they do. But in the presence of acidic protons, they react as strong bases. So our protic solvents were mostly alcohols, water. A proton on a nitrogen is acidic enough. Of course, this proton is more acidic than this one. Hey, there's the acidic hydrocarbon proton on an alkyne. And if we have solvents that have these groups, the organometallic reagent's going to react with them. Here's carbon monoxide. Here is cyanide. Here's cyanide again. Now, of course, one might want to do that and form some interesting compounds. You're going to form a new carbon-carbon bond here. Form a new carbon-carbon bond here. So you can get to some amines and maybe some ketones or other alcohols. So here is the acid-base chemistry. What is the pK of an alkane? I told you it was 50. They're saying greater than 45. Oh, here's the about 50. An alkane is the weakest acid known to mankind. That means ethyl lithium or ethyl magnesium bromide, these are about the strongest bases man can produce. So of course, in the presence of protic solvent, you just protonate the alkyl halide. And that might typically be a waste of your money. So here's an organolithium compound. If you tried to use this as a solvent, this hydrogen just comes off and protonates that. Then you have this lithium salt. Same thing here. This thing's acidic. It's just going to protonate where that lithium is. Any questions? But there's lots of material. I've asked lots of questions and I got lots of blank looks. But I've foreshadowed a lot of things that could be on there. Any reaction that forms an alcohol. Fun packed 2 days. All right, we'll stop there.